Good afternoon. Today we're going to look at the tan function. So we've previously looked at sine and cos and their related graphs. So now it's time to think about, well, we've got sine and cos. Well, there's always a third one, which is tan. So what does the graph of tan look like? And to understand tan, you have to understand what makes tan the way it is. All right, so if you guys remember that tan is actually represented by two other functions. Tan of theta is equal to sine of theta divided by the cos of theta. And with that creates an interesting problem. Because if you think about a normal tan graph, if you think about a normal cos graph, starts high, goes down low, goes back up, like that. That means that our graph crosses, it actually full-on crosses the x-intercept. It has x-intercepts. So it has times when the y value is equal to 0. So you have an answer of 0 of cos theta. And that's not good. Because what happens when you try and divide by 0? Think back to the work that you've done with hyperbolas. If you're ever doing, sine, cos, and tan, or you're ever doing sine and cos, and you get cos of 0, and you try and divide something by 0, think about when you go and you do 1 on x, and you think about what the graph of that looks like. It looks like this. What are these things called? For when you have either a divide by 0 error or a completely or an illogical mistake, you get asymptotes. So tan has asymptotes, and the interesting thing about tan is that because it is a circular function, how many asymptotes does it have? It's actually going to have infinite asymptotes. If I just wanted y equals tan of x, and I'm looking at x being all real numbers, then I can have infinitely many asymptotes, because I'm going to infinitely hit that point where cos of x is also 0. So what's important to recognize is that when we are talking about tan, we want to make sure that we're working inside a predefined space. So restricting the domain to think about your problem more logically is going to make life so much easier. So, behind me is my Kaz, and it is time to introduce you to our good friend Tan. Alright, my Kaz is in Radians mode, and here we go. Helps if I check the item. So that's tan. It says hello. Now what I'm going to do is I'm going to change things a little bit. We're going to look at 0 to we'll go to 4 pi. And we're going to have a scale of, we'll go pi on 4. So, how many full loops do I do inside 4 pi? Remember that my window is currently set to minimum of 0 and a maximum of 4 pi. How many full loops does it do? So that's the thing. Where does the period of a tan graph start and end? Now, because we're working with 0, we're starting at 0 and we're working along. So what I'm going to do is I'm going to take a screenshot of this and bring it over to my whiteboard so that I can scribble on it. If I wanted my graph, if I was starting from here, I go all the way up. I hit, this is clearly where my first asymptote is. And then I move across and I come all the way back up. And there's my next intercept. And repeat. Intercept. All the way up. How many loops have I done? Remember that I start from here. The full loops, now it's not 5, it's 4 full loops. So I have one here, and then I have another one here, there, and there to finish off. So I have 4. So this is between 0, 4 pi. Now, I said my markings were pi on 4. So, because I've vandalized that one, I'm going to bring up another one. Look, if you position them correctly, they are... Yeah, I will adjust the roll in a moment. So each of these little notches that I'm putting along here, do them in a different color so that you can see them. Each one of these is pi on 4. And remember, this is a normal tan graph. So this is just tan of x. There's no dilations, there's no shift or anything like that. Looking at this graph here, what is the period of this graph? What makes it different? Remember that the period of the graph is the time it takes to complete one full loop. So if I measure from here to here, how many pi have I gone along? Pi and 4, 2 pi and 4, 3 pi and 4, 4 pi. Now I'm already back to where I started, so the distance between here and here is just pi. What's the value of n that I have in here? What's the coefficient of x? It's 1. So from this, the period of tan theta is not 2 pi on n, it is pi on n. So this is slightly different to sine and cos because it is pi on n, not 2 pi on n. And then, where are our asymptotes? So where's the first one? It's at, so that's pi on 4, 2 pi on 4. So what's this? 2 pi on 4. So that's going to become pi on 2. So you're going to have an asymptote at pi on 2. The next one is going to be pi apart. So it's going to be 3 pi on 2, 5 pi on 2, and 7 pi on 2. So each time to get the next one, you are adding pi. So, what I want to introduce you to is a couple of formula that are related to how we work with tan and tan graphs and like little things to remember when you're working with them. So, the asymptotes, so if I have a function, so if I have a function for tan, f of x equals a tan nx, this is a dilation factor. This will not influence the number of asymptotes or the number of intercepts. It will merely change the shape of the graph. I have n, which influences the period. So in this case, n is 1, so the graph repeats itself every pi. Now, what we do also have is we have a general formula for all of the asymptotes. All right? And this is going to look a little weird. The asymptotes have a solution x, because x is where our intercepts are going to be, x equals 2k plus 1 pi over 2n. K is any integer All right, you guys remember the word integer? Means any whole number. So what that means is in this case of what we got going on up here, n is 1 still. So that means that the intercepts are going to be at (2k plus 1 pi over 2). The first intercept you run into, k is 0. 0 is an integer. So if I put 0 into this little formula here, well, then I have 2 times 0 plus 1. So the first one I have is pi on 2. If I do k is 1, 2 times 1 is 2, plus 1 is 3. X equals 3 pi on 2. And I keep going and going and going, and I will spit out these numbers, and then what's the next one? What's the next one? What's the next one? I could, if I wanted to, go, well, okay, what about if I wanted the 12th? If I wanted k equals 12, well, the formula would go in. K equals 12, and it would equal 24 plus 1 pi over 2. So it would be 25 pi on 2. And then you can also get all the ones that go backwards by just working backwards from 0. Minus 1, minus 2, minus 3, minus 4. And you can spit them all out. The other thing that's also important is your x intercepts are also, so how many x-intercepts do I have? I have infinitely many. And I can also, are also found with a rule. T equals k pi on n. So in this case here, that we've got at the top there, n is 1. So I would have t equals 0, t equals pi, t equals 2 pi, 3 pi, and so on. Because k just keeps going up. And then you would just keep going and going and going and going and going. All right. Use your CAS to help you. All right. Use your CAS to help you. Now, when you are drawing these, so this is the one that I've got off the CAS. What you need to do, so for example, if I wanted you to draw this by hand, you would have to have your axes. You would have to also then clearly label all of the intercepts. So that's 0, pi, 2 pi, 3 pi, and 4 pi. And you would also have to draw in all of your own intercept, all of your own asymptotes. And then, as the absolute kicker, you have to then go and actually label the equations for all your asymptotes. The other thing to remember about tan is that the asymptotes are always halfway between intercepts. All right, that's one of the easiest ways to remember where to put one. So if you know that you've got an intercept at 0 and an intercept at pi, well then your asymptote is going to be halfway between that. So if we change the period of the graph, if we change it to something different, we can still remember that. If we can find where our intercepts are, we can then go, well, halfway between the intercepts is going to be where our asymptotes are. All right.